Well, I'm Giorgos Kollias. I work for Logic Blocks, and I'm going to give you an overview about the Logic Blocks engine, how we do benchmarking, and a few more specific graph benchmarks. Is it working?
Nope.
No.
Okay. No.
I have one.
It's a decoy.
I can share mine.
Oh, it's okay, thanks. So, yeah, good idea. Here we are. So, firstly, two words about Logic Blocks. Louder, please. Okay, I'll try. It mainly develops application for planning, prediction, and optimization domains, and it has mainly customers from big retail customers from the United States, and also recently it's involved with other projects, and more specifically with this project, Muse, from DARPA, which is about large-scale static analysis. So here we see a recent map from October with most of the existing database systems we have. Probably it's neither accurate nor complete. So we can see that there are tons of specialized systems for each particular need. Probably that specialization trend started at mid-90s, where there was some innovation in the DB community, and it started developing a lot of specialized systems. A good example of that are column stores, more specifically MongoDB, which is very, very fast on doing analytics. And as later Professor Stonebreaker stated, all these specialized purpose-built systems are 10 to 100 times faster than general-purpose ones. But of course, we know if we are going to use many of these specialized systems, we have increased cost, increased maintenance cost, tuning cost, development cost, etc. And of course, these systems are only worth it if they are indeed 10 or 100 times better. A few years ago, more and more systems started integrated different specialized technologies into single systems. Dr. Bones wrote about that a few years ago, and he mentioned two specific examples, Microsoft SQL Server and OpenLinks Virtuoso, that try to combine both column and row store technologies. So, does it mean that if we combine more and more specialized technology, if we put them together, we have a one-size-fits-all system? Probably not, because we need the expertise to tune each of them. Here is where Logic Block comes in. Its engine is designed to be one-size-fits-all system, in the sense that it's less than 10 times worse than any specialized system, but without too many tuning knobs. It tries to be transparent to the user. So let's see which technologies enable Logic Blocks to be such a system. First of all is its language. It's called Logical. It's a datalog variant, so it's declarative. It supports recursion. On top of that, it supports aggregation and recursion and negation and recursion. Of course, it has integrity constraints. Also, it supports event handling, which is similar to SQL's triggers. And also, it supports incrementally maintained rules, where rules are like materialized views in the SQL world. Probably we all agree here that the current pairwise joins of most relational databases are not sufficient for all different workloads. That's why Logic Blocks uses a novel join algorithm. It's called leapfrog tree join. It's a worst-case optimal join algorithm, and it does multi-way join. So it joins all queries, predicates, relations simultaneously. You can imagine it as a variant of a short merge join, and you can see more details in this ICDT paper that was presented this year in Athens. And also recently, another join algorithm was implemented on top of the core logic blocks engine. It's called Minesweeper. Again, it's worst case optimal, and again, it's a multi-way join. And here is the PODS paper.
Which one's better?
I can't tell.
Where's the hash join?
No hash join. So right now the default one is a leapfrog tree join, and it's more production ready, and probably does better in most of the cases. As we said, logic block supports incremental maintain rules. So whenever a rule symbols change, the work to be done to maintain that rules is going to be proportional to the number of changes. Also, for example, Postgres added recently materialized views, but you have to maintain them manually to refresh them explicitly. Also, consistency is very significant for large applications. So, logic blocks has log-free scalable transaction processing that achieves full serializability. And again, here is the paper for more details. In order to take advantage of all these many core systems today, we have intra-query parallelism, which means that a query's domain is partitioned into many small subdomains. And ideally, these subdomains are going to require the same amount of work, and all these subdomains are consumed from the query in parallel. So here you can see in that graph, each line is a core, and all these small blue boxes are subdomains. And here you can see that there is no core essentially idle, and we achieve almost full CPU utilization. Let's see a little bit how we do benchmarking at Logic Blocks. So first of all, let me mention which benchmarks we run. We run TPC-8 and TPC-DS for OLAP style workload. We run TPC-C and various micro benchmarks for all TP workload. And also, we run TPC-C8 and II bench. We are to combine these two kind of workloads. We have both analytical and transaction workload here. Essentially, TPC-C8 is a merge of TPC-8 and TPC-C. On the graph side, we have chosen LUBM and a few specific graph queries, click and path. So we chose we handpicked these ad hoc queries mainly because there is no standard graph benchmark. So hopefully LDBC benchmarks are going to fill that gap here. And also we have wrapped some real-world parts of some real-world applications into some benchmarks, and we run them continuously. So for each of these benchmarks, we have several variants at multiple levels. So for example, at the physical layer, we have two IA bench variants. One uses a normalized schema, and one uses normalized to see how each of them perform. Again, in the logical layer, for example, we have two variants of the TPC-C8 aggregate queries. One of them is modeled using rules, and the other queries to see how their performance differ. And also, several benchmarks uses several different API abstractions. So mainly we do that to see where our bottlenecks lie, and to make sure to test as many features as we can. Here is a small screenshot of our internal reporting site. So for example, here you can see results for TPC-8, TPC-DS, and micro benchmarks. We have multiple variants, as I said, for each of them. And we report the current, the latest results. And also we collect historical data, and they are presented either by date or by commit. So for example, here is a not so recent example where we detected some performance regression that we had in our engine. And now let's go to some graph benchmarks. We have ported LUBM in logic blocks. Of course, logic blocks doesn't have any semantic web facilities, capabilities, but we were able to capture most of our schema using logical rules, constraints, and subtyping, which supports. And let me note here that its dataset scale factor denotes the number of universities in this ontology, and datasets grow linearly. And we have 14 queries on this benchmark. 10 of them have a fixed result set regardless of the scale factor. And also they are usually accompanied with a few single joins. 2 of them have result sets that grow linearly with the scale factor, and they have one-click join. And the rest do have, again, result sets that grow linearly with the scale factor and have no joins at all. Let me focus on the first category, on the fixed result set queries. So, as I said, all these queries return the same result set regardless of the scale factor. So, the usual graph database's argument here is that you can go from one node to the neighbor one in constant time. Ideally, in a good graph database, these queries should take the same time across all different scale factors. And you can see in this chart that indeed LB takes constant time for all these queries. So it might imply that LogicBlocks is a good graph database. So we model each edge as an index binary relation, and combining that with the efficient leapfrog tree join that I mentioned before, we achieve constant time hops. And last, we have the LUBM click queries. It's query 2 and query 9. Here I put a comparison with Virtuoso. For example, on query 2, LogicBlocks is quite faster than Virtuoso, while on query 9 we can see that Virtuoso is a bit faster than LogicBlocks here, until to scale factor 1000. Here is query 9, which is a click essentially, how it's expressed in logical and sparkle. Both of them are declarative and they are very terse and laconic. And here we have some more recent pure click results. They are for an upcoming paper we are preparing. So here we have 3-click and 4-click on the LiveJournal dataset from, which is quite big, 1.7 gigabytes, I think. And we run these queries over incremental parts of this dataset. And I'm not going to go very deep here. The red line here, and here is a LogicBlocks engine using the leapfrog tree join, and it seems to scale better than the rest of the systems. We have tried quite a few systems here, so some of them, let me mention some of them. It's MongoDB, it's Virtuoso, it's Redshift, it's Postgres, and another in-memory hybrid database.
What's your physical representation? Is it like multi-column rows, or is it triples, or?
Well, typically it's a row store.
Right. Okay. So you got multiple columns consecutively in memory, and that's what? Yeah.
So it's a row store, right?
Yes.
Okay. Yeah.
Okay.
And we try to mimic column stores at the logic layer.
All right.
Okay. So let me mention LogicBlocks has a quite extensive collaboration network. Let me here show quite a few of their collaborators, current and past. So that's it for me. Thanks.
Questions or remarks for LogicBlocks? So is this is there a single engine that is always used, or is this are there subsystems in this engine that are intelligently used?
Let's say it's a single engine.
A single engine.
Yeah,
Right,
but
so,
it's yeah. Sorry.
yeah, so you do recursion, so therefore you must be able to express things like shortest path and graph traversals and stuff like that, transitivity,
Yeah.
by recursive data log.
Mm-hmm.
Okay. Can you tell us more about this? About, let's say, breadth first, depth first, all these diverse variations that you could conceivably do. I mean, how do you do that?
Well, first of all, I'm in the benchmarks team. I'm not in the runtime, the core runtime, so I don't know exactly the implementation details. I know we are tuning them. All the,
It's forward chaining for the most part, right? Or backward?
I guess it's forward, but I'm not 100% sure.
Okay, so yeah, okay, that is of course tricky if you want to do shortest paths or stuff like that. Okay, so the question might not be appropriate. But okay, I'd like to know about this stuff anyway.
Is there a paper that describes logic blocks? So this upcoming paper, is it going to?
No, there are tons of papers that describe parts of logic blocks. So I showed a few of them. Here's one about transactions. Here the other one about incremental maintenance, and here about the core join algorithm. All of them, not all of them, 3 of them are written from Todd Belhuizen.
Yeah.
Mm-hmm.
Okay, so but these are okay. These are all algorithmic, but system level.
Yeah, there is nothing like that. But
Do you have any plans to support Sparkle?
probably not. Are you interested in?
He's a competitor.
Just curious.
He just
Oh,
wants to know
really?
if you're going to his space or not.
Okay.
The answer should be yes.
Yes.
It's working in the labs.
Okay, so well, thank you again, and
Thanks.